Next, we'll look at another problem of the same type. So we want the area bounded by these two curves in this x region. So again, it's a good idea to graph everything first, just so that you know what the rough shape of everything is and which function should be the top function. So we'll start with y equals 8 because that's nice and easy to graph. That's just going to be the horizontal line up here at y equals 8. And if it helps, you can also graph these side curves here. So the boundary for x would be x equals -4. That's the vertical line at x equals -4. And then the other x boundary will be here at +4. So we can also graph x equals +4. So we're looking for the region bounded by these, and also y is equal to -2x. So y equals -2x, that's going to be a line that has the y-intercept 0. So it'll go through the origin. And then if you want a second point that lives on the line, you could maybe just plug in an arbitrary x value. Let's just choose 4 again. So if I plug in x equals 4 into this line, then what I would get is y is equal to -2 times 4, which is -8. So that would live down here. So that's a second point that lives on our line, and therefore the graph of our line looks something like this. This is y is equal to -2x. Now here it's a little bit important what this intersection point is up here. So we need to know whether y equals 8 stays on top throughout this entire region that we're considering from here to here, or whether the line starts to cross over and become the dominant function inside of this region. So I need to know what this intersection point is. Anytime you want the intersection between two curves, like these two curves, you can just set the y values equal to each other. So if you need the intersection point, you would set one y value equal to the other y value, and then solving for x will tell you the x coordinate where they intersect. So if I divide both sides by -2, I would get that x is equal to -4. So it's true that these do intersect here at x equals -4. But that's good, because what that means is that y equals 8 is going to be the upper function throughout this whole region. So from -4 to +4, y equals 8 is always bigger than y equals -2x. So that means that if we want to compute the area, we just need to integrate from our lower x bound to our upper x bound, and we take the upper function minus the lower function. So this will be 8, which is the upper function, minus the lower function, which is -2x. So that's upper minus lower. And now we will integrate. So, well, let's first just simplify the inside so that we don't have to deal with signs. So this would be 8 plus 2x, and now we'll integrate that. So the antiderivative of 8 is 8x. The antiderivative of 2x, you can add 1 to the power so that it becomes an x squared, and then divide by the new power if you'd like. Or you can just remember that the antiderivative of 2x is x squared. So either way, what we should get is this antiderivative, and we're still evaluating from -4 to 4. So I want to evaluate that, and if you'd like, just to clean things up a little bit, I'll rewrite this. So that's 8x plus x squared, and we're evaluating this from -4 to 4. So we plug in the upper bound, so that would be 8 times 4 plus a 4 squared. And then we subtract the evaluation at the lower bound. So that would be an 8 times a -4 plus a -4 squared, if we just plug in -4 into our antiderivative. So that's how we evaluate. We just plug in the upper bound and then subtract what we get when we plug in the lower bound. And now we can clean this up a little bit. So 8 times 4 is a 32, plus 4 squared would be a 16. And then we'll get minus on the inside of this set of parentheses, we have 8 times -4, which would be a -32, plus a -4 squared, which is a 16. So that would be 32 plus 16 minus a -16 on the inside of the parentheses, So that's 32 plus 16 plus another 16, that gives us 64 in total. So we'll have 64 square units of area in this triangular region. And by the way, that makes sense because if you want, you can compute this area. So notice the region that we're computing the area for is a triangle. We can also compute, in this case, the area geometrically by just noting that this side length is 8, and this side length along the height is 16. And the area of an 8 by 16 triangle should be 64. So we do end up getting the correct area in this case, but this technique is a lot more powerful than just being able to compute things like areas of triangles or trapezoids, because in this technique we can compute areas like the area bounded by this region here. Sorry, bounded by those curves. So we'll be able to compute areas that we didn't know how to compute in the ordinary geometric way, and we'll do that in our next example.